Hey everyone, Dr. Crayhay here. In this Chapter 10 lecture, I'll talk about interrogating causal claims using the four validities. Chapter 5 discusses validity in much more depth than we'll go into right now, so if you need to review that, go ahead and do so. But in this Chapter 10 lecture, I just want to give you a general framework to interrogate those causal claims using four validities. So here we have listed construct, external, statistical, and internal validity. So remember, construct has to do with how well your variables have been measured. External has to do with generalizability, how representative is your sample, all those kinds of questions. Statistical validity has to do with the size of your effect. And then of course your probability, your p-values, all those kinds of things. And then internal validity, so you're looking for any kind of external causes, any alternative explanations, all of those sorts of things. So in looking at a causal claim in particular, so you're saying one thing causes another. These are some specific questions that you can ask. So first of all, how well were the variables manipulated? How well were the variables measured? How did they measure depression? How did they try to induce depression in these people? Do you think that's an effective manipulation? Has it been used before? When it was used before, was it successful? All of those kinds of questions. External validity, to whom or what can the causal claim generalize? So in the study, who are their participants? How did they find these participants? Do those participants represent a larger group of people? Is it the larger group of people that they're trying to claim they represent? A lot of times in psychology, we'll use what's called a convenience sample, and so we'll have college undergraduates complete our research studies, and then we try to claim that the results from this study generalize to the entire U.S. population. That's a problem with our external validity because college students are not typically representative of everyone in the United States. Statistical validity, how well do the data support your causal conclusion? So maybe you're claiming some kind of, one thing leads to another, but then your effect size is really, really, really small. That's a problem. Maybe your p-value is too high, so you have to look for all of those things when you're evaluating these causal claims. And then internal validity. Are there alternative explanations for the outcome? This is probably the most important validity for experiments. So you're saying one thing causes another. You need to look for any alternative explanation. One example that I like to use a lot in my classes is, there is a true correlation between average ice cream sales in a month, say, and the number of drownings. So some people would interpret that as, ice cream causes drowning. And that would make it a causal claim. Well, you have to consider alternative explanations. There's a very clear one here, which is heat. When the temperature goes up, people buy more ice cream and they also go swimming more. And so because they're doing those two things more, it looks like they have a relationship. But in fact, it's just, more people going outside, more people swimming, all of those kinds of things that's drawing the effect. It's not the fact that people are eating ice cream and then going swimming. There's no causal connection there. So you have to interrogate, you have to consider any alternative explanations. This is not always easy, but it is the most important. So here are a few discussion questions to consider, and I'll just briefly touch on each one. The first being, you always need a control group in an experiment. So first of all, what is a control group? Typically this will be a group that does not experience any kind of treatment. They don't have any kind of manipulation. They just go about their everyday life, and we want to see how things change. So say you bring in a group of people that are depressed. You divide them into two groups. You have a treatment group that's going to start taking, Prozac or something for a couple of weeks, and then you'll measure their symptoms at the end of that period. Your control group, on the other hand, they wouldn't do anything. So they'll just continue on with their everyday life, and then you'll measure depression at the end of those 2 weeks and you'll compare. So control groups can be very useful, but they're also problematic and you don't necessarily need them. So when you're comparing something against nothing, you're probably going to get an effect. Oftentimes when control groups are used, this is what we do. We compare, a drug versus absolutely nothing. A better way to be doing this would be looking at different experimental groups. So maybe we want to test Prozac against Wellbutrin against exercise, and then see how depression changes over those 2 weeks. So you don't necessarily have to have a control group. You just need a group to compare against. It doesn't have to be a no treatment group, though. You always need a pretest in an experiment. So this is the idea that before anything starts, you give a pretest, and then at the end of it, you give a post-test. Sometimes you'll want a pretest post-test design, but oftentimes it's unnecessary. If you've used random assignment, you really don't have to worry about pretests as much. So random assignment means I have people come into a room and I flip a coin, and if you get heads, you're in group A, B, tails, you're in group B. So I've randomly assigned people. Theoretically, if you've done this, you should even out all of the group differences so that you have two approximately equal groups. So it's very unlikely that all of the females would end up in one group, males in another group, or all of the really high IQ people in one group, low IQ in another. All of those kinds of differences should wash out with your random assignment. In those kinds of cases, you wouldn't necessarily need a pretest. Pretests can be very useful in certain circumstances, but you don't always need them. Okay, lastly, you need a random sample in an experiment. Again, this is sometimes true, but not always. So depending on what you're doing, you might want to take a random sample, but maybe you want, like the first example I was using, you want to treat people with depression. Well, that wouldn't necessarily be a random sample because you need targeted individuals. So you want a specific kind of sample. You might want a stratified sample, so you want to accurately represent whatever population you're trying to generalize to. So you'll pull in, so many people of this ethnicity, so many of each gender, so many of each education level, and so you'll do some pretty complicated forms of sampling. So a random sample, again, in some situations, that's the way that you want to go, but not necessarily in every single situation. So it depends on the purpose of your research, it depends on your hypotheses, who you're trying to generalize to. So it's not an always kind of thing with all three of these points.